In collaboration with F1 in Schools, Airbus would like to welcome you on board again. Building on what you have learned in the first video, let's dive deeper into aerodynamic design. In our last video, we explored the forces acting on a Formula 1 car and our A320 plane. Now we will discover how aerodynamic design affects those forces. Let's take a closer look at the wing section. An optimized wing design turns the surrounding airflow to provide sufficient lift with as little drag as possible. But what does that really mean? Well, let's imagine our wing section was a simple rectangle with the same frontal area. Let's see what happens when air flows past a rectangle. Looks like quite a mess. What's going on here? You can see that the flow doesn't neatly follow the profile of the rectangle. The flow seems to be really struggling around the corners. This is known as flow separation. A low pressure region is created at the rear of the body due to this separation. The higher pressure at the front compared to that at the rear pushes the body backwards. This force is influenced by the shape and is referred to as form drag. Form drag is part of the parasitic drag mentioned in our last video, so let's see if we can reduce it. Keeping the same frontal area, we can round off the corners where the flow is struggling to remain attached. You can see that the separated wake at the rear is now reduced. But can we improve the flow even more?
Yes. Common airfoils are designed to minimize drag by adjusting the roundness of the leading edge and sharpness of the trailing edge. Now we understand that controlling form drag is all about managing sharp corners and extreme curvature. Aerodynamicists have quantified drag using the following formula. The drag force on the body depends on fluid density, in this case the density of the air, the speed of the object. A reference area, in our case, the frontal area, and last but not least, the drag coefficient. When we gradually transformed the rectangle into the airfoil, we've kept the frontal area, the fluid density, and the flow speed exactly the same.
So the only thing that could have changed was the drag coefficient, right?
Exactly. In fact, the drag coefficient is a measure of the physical effects we've just discussed. Let's visually recap what we've done. Notice the change in the drag coefficient as we manipulate the shape. So, the key to reducing drag is to minimize the drag coefficient.
Cool. And how do we generate lift?
Well, a simple way to do this is to introduce an angle of attack. Creating lift is all about turning the surrounding airflow to achieve a higher pressure on the bottom surface than the top surface, as presented in our last video. We can obtain even more lift by increasing our airfoil's curvature, or camber. However, we've got to be careful our curvature doesn't create too much drag.
The same aerodynamic principles literally shape our design across the aircraft. Our goal is to achieve an optimal balance between lift and drag. In addition to shape, surface finish is also extremely important in minimizing skin friction drag. Our Airbus A330neo applies modern and highly specialized manufacturing techniques to achieve an impeccably smooth surface finish. So how can you apply these ideas to your F1 in Schools car?
Since your F1 car will travel in a straight line, drag, rather than downforce, should be your primary focus. To be the fastest car on the track, you need to reduce the drag and weight of your car as much as possible, since the amount of thrust is fixed by the CO2 cartridge. An effective way to minimize drag is to identify the areas in your car where flow separation occurs. In this example, you may find vortices around corners where the flow cannot follow the shape of the car. Don't underestimate the impact of small changes in the geometry. These changes can get rid of these annoying vortices and reduce the drag of the car. Be careful to follow the dimension restrictions of the car for your category. Looking from the side, you'll find many areas of improvement. Here's a tip: front wings are very useful to redirect the air and reduce drag. Don't forget the interaction between the airflow around the car and the CO2 exhaust. Because of this, following the design of a real F1 car is not always the best solution.
We've given you some of the tools, now it's your turn to be creative. To discover more techniques to improve your car's performance, don't miss our next video. Want to find out more about career opportunities within Airbus? Please visit our website in the link below.